Welcome to nucleophilic substitution. Nucleophilic substitution is the chemical reaction in which a leaving group X is replaced by an attacking nucleophile. There are two mechanisms for nucleophilic substitution, SN1 and SN2. First, let's look at SN2. SN2 is a one-step bimolecular mechanism. In this case, iodine is the X group. The nucleophile, with its lone pair of electrons, attacks the partially positive carbon atom 180 degrees away from the CI bond. The nucleophile forms a bond with the carbon at the same time that the CI bond breaks. This results in the formation of the trigonal bipyramidal transition state, shown in brackets. This state cannot be isolated. In this state, two partial bonds are formed with the nucleophile and the leaving group, which are 180 degrees apart, while the remaining groups are in the same plane. Following this, the CI bond breaks completely and the nucleophile's bond forms. Since the nucleophile attacked the carbon from the opposite side of I, there is inversion of the stereochemical configuration about the carbon center. Next, let's look at SN1. SN1 is a two-step unimolecular mechanism. The first step involves the cleaving of the Cl bond, forming a halide ion and a trigonal planar carbocation intermediate. Due to its planar structure, the nucleophile can attack the carbocation equally from above and below the plane, hence forming a racemic mixture if the reaction started off with a single enantiomer of an asymmetric molecule. Now, let us look at the different factors that affect the rate of reaction in these nucleophilic mechanisms. The first factor is steric hindrance. Steric hindrance on the carbon by bulky R groups hinders the approach of the nucleophile in SN2 reaction, slowing down the rate of reaction. The bulkier the groups, the more sterically hindered the approach of the nucleophile, hence the slower the rate of reaction. The second factor is inductive effect, specifically positive, which means that the R groups are electron donating in nature. In SN2, the bulkier the R groups, the stronger the positive inductive effect, reducing the partial positive charge on the carbon to a greater extent, hence making it less susceptible and attractive to a nucleophilic attack. Thus, the rate of reaction is slower. On the other hand, in SN1, the stronger inductive effect by the bulkier groups on the carbocation stabilizes the carbocation to a greater extent by dispersing the positive charge more. Hence, the rate of reaction for SN1 increases with bulkier groups attached to the carbon. In addition, in the SN1 mechanism, there is steric acceleration as the tetrahedral halogenoalkene converts into a trigonal planar carbocation. The R groups are further apart, leading to a release of steric strain. Hence, SN1 is favored due to the increased stability as the reaction progresses. However, in the case of SN2 reactions, the steric interaction in between bulky R groups increases, especially in the trigonal bipyramidal state where there are 5 groups crowding around the central carbon. This leads to an increase in energy level of the transition state, indicating instability of the structure.